Chapter 34 of Astronomy, the Science of the Heavenly Bodies. Read by Light Crystal. Astronomy, the Science of the Heavenly Bodies, by David Todd. Life in Other Worlds. Popular interest in astronomy is exceedingly wide, but it is very largely confined to the idea of resemblances and differences between our Earth and the bodies of the sky. The question most frequently asked the astronomer is, have any of the stars got people on them? Or more specifically, is Mars inhabited? The average questioner will not readily be turned off with yes or no for an answer. He may or may not know that it is quite impossible for astronomers to ascertain anything definite in this matter. Most interesting as it is, what he wants to find out is the view of the individual astronomer on this absorbing and ever-recurring inquiry. We ought first to understand what is meant by the manifestation here on the earth called life, and agree concerning the conditions that render it possible. Apparently they are very simple. We may or may not agree that a counterpart of life, or life of a wholly different type from ours, may exist on other planets under conditions wholly diverse from those recognized as essential to its existence here. The problem of the origin of life is, in the present state of knowledge, highly speculative and hardly within the domain of science. Here on Earth, life is intimately associated with certain chemical compounds, in which carbon is the most common element without which life would not exist. Also hydrogen, oxygen, and nitrogen are present, with iron, sulfur, phosphorus, magnesium, and a few less important elements besides. But carbon is the only substance absolutely essential. Protoplasm cannot be built without it, and protoplasm makes up the most of the living cell. Closely related to carbon is silica also. As a substitution in certain organic compounds, protoplasm is able to stand very low temperatures, but its properties as a living cell cease when the temperature reaches 150 Fahrenheit. Animal life, as it exists on the Earth today, appears to have been here many million years. The paleontologists agree that all life originated in the waters of the Earth. It has passed through evolutionary stages, from the lowest to the highest. Throughout this vast period, the astronomer is able to say that the conditions of the Earth, which appear to be essential to the maintenance of life, have been pretty constantly what they are today. The higher the type of life, the narrower the range of conditions under which it thrives. Man can exist at the frigid poles, even if the temperature is 75 degrees below Fahrenheit 0, and in the deserts and the tropics. He swelters under temperatures of 115 degrees, but he still lives. At these extremes, however, he can scarcely be said to thrive. We have, then, a relatively narrow range of temperatures which seems to be essential to his comfortable existence and development. We may call it 150 degrees in extent. Had not the surface temperature of the Earth been maintained within this range for indefinite ages, in the regions where the human race has developed, quite certainly man would not be here. How this equability of temperature has been maintained does not now matter. Clearly the Earth must have existed through indefinite ages in the process of cooling down from temperatures of at least 6,000 degrees. During this stage, the temperature of the surface was Earth-controlled. Then this period merged very gradually into the stage where life became possible, and the temperature of the surface became, as it now is, Sun-controlled. How many years are embraced in this span of periods, or ages, we have no means of knowing, but of the sequence of periods and the secular diminution of temperature we may be certain. Then there is the equally important consideration of water necessary for the origination, support, and development of life. We cannot conceive of life existing without it. On the Earth, water is superabundant, and has been for indefinite ages in the past. There is little evidence that the oceans are drying up, Although the commonly accepted view is that the waters of the Earth will very gradually disappear. Water can exist in the fluid state, which is essential to life, at all temperatures between 32 degrees and 680 degrees Fahrenheit. Air to breathe is essential to life also. The atmosphere which envelopes the Earth is at least 100 miles in depth, and its own weight compresses it to a tension of nearly 15 pounds to the square inch at sea level. This atmosphere and its physical properties have had everything to do with the development of animal life on the planet. Without it and its remarkable property of selective absorption, which imprisons and diffuses the solar heat, it is inconceivable that the necessary equability of surface temperature could be maintained. This appears to be quite independent of the chemical constituents of the atmosphere, and is perhaps the most important single consideration affecting the existence of life on a planet. If the surface of a planet is partly covered with water, it will possess also an atmosphere containing aqueous vapor. Heat, water, and air. These three essentials determine whether there is life on a planet or not. Of course, there must be nutrition suitable to the organism, mineral for the vegetal, and vegetal for the animal. But the narrow range of variation appears to be the striking thing. Relatively but a few degrees of temperature, and a narrow margin of atmospheric pressure. If this pressure is doubled or trebled, as in submarine caissons, life becomes insupportable. If, on the other hand, it is reduced even 1/3, as on mountains even 13,000 feet high, the human mechanism fails to function, partly from lack of oxygen necessary in vitalizing the blood, but mainly because of simple reduction of mechanical pressure. If, then, we conceive of life in other worlds, and it is agreed that life there must manifest itself much as it does here, our answer to the question of habitability of the planets must follow upon an investigation of what we know, or can reasonably surmise, about the surface temperatures of these bodies, whether they have water, and what are the probable physical characteristics of their atmospheres. We may inquire about each planet, then, concerning each of these details. The case of Mercury is not difficult. At an average distance of only 36 million miles from the Sun, and with a large eccentricity of orbit which brings it a fifth part nearer, conditions of temperature alone must be such as to forbid the existence of life. The solar heat received is 7 times greater than that at the Earth, and this is perhaps sufficient reason for a minimum of atmosphere, as indicated by observation. If no air, then quite certainly no water, as evaporation would supply a slight atmosphere. But according to the kinetic theory of gases, the mass of Mercury, only a very small fraction of that of the Sun, is inadequate to retain an atmospheric envelope. If, however, the planet's day and year are equal, so that it turns a constant face to the Sun, surface conditions would be greatly complicated, so that we cannot regard the planet as absolutely uninhabitable on the hemisphere that is always turned away from the Sun. Venus, at 67 millions of miles from the Sun, presents conditions that are quite different. She receives double the solar heat that we do, but possessing an atmosphere perhaps 3-fold denser than ours, as reliably indicated by observations of transits of Venus. The intensity of the heat and its diffusion may be greatly modified. What the selective absorption of the atmosphere of Venus may be, we do not know, nor is the rotation time of the planet definitely ascertained. If equal to her year, as many observations show, and as indicated by the theory of tidal evolution, there may well be certain regions on the hemisphere perpetually turned away from the Sun, where temperature conditions are identical with those on the tropical Earth, and where every condition for the origin and development of life is more fully met than anywhere else in the solar system. Whether Venus has water
Distributed as on the Earth, we do not know, as her surface is never seen, owing to dense clouds under which she is always enshrouded. Her cloudy condition possibly indicates an overplus of water. Is the Moon inhabited? Quite certainly not. No appreciable air, no water, and a surface temperature unmodified by atmosphere, rising perhaps to 100 degrees Fahrenheit during the day, which is a fortnight in length, and falling at night to 300 degrees below zero, if not lower. Is Mars inhabited? The probable surface temperature is much lower than the Earth, because Mars receives only half as much solar heat as we do, and more important still, the atmosphere of Mars is neither so dense nor so extensive as our own. Seasons on Mars are established, much the same as here, except that they are nearly twice as long as ours, and alternate shrinking and enlarging of the polar caps keeps even pace with the seasons, thereby indicating a certainty of atmosphere whose equatorial and polar circulation transports the moisture poleward to form the snow and ice of which the polar caps no doubt consist. There is a variety of evidence pointing to an atmosphere on Mars of 1/3 to 1/2 the density of our own, an atmosphere in which free hydrogen could not exist, although other gases might. The spectroscopic evidence of water vapor in the Martian atmosphere is not very strong. It is very doubtful whether water exists on Mars in large bodies, quite certainly not as oceans, though the evidence of many small lakes is pretty well made out. With very little water, a thin atmosphere and a zero temperature, is Mars likely to be inhabited at the present time? The chances are rather against it. If, however, the past development of the planet has progressed in the way usually considered as probable, we may be practically certain that Mars has been inhabited in the past, when water was more abundant and the atmosphere more dense, so as to retain and diffuse the solar heat. Biologists tell me that they hardly know enough regarding the extreme adaptability of organisms to environment to enable them to say whether life on such a planet as Mars would or would not keep on functioning with secular changes of moisture and temperature. The survival of a race might be ensured against extremely low temperatures by dwelling in sub-Martian caves, and sufficient water might be preserved by conceivable engineering and mechanical schemes. But the secular reduction of the quantity and pressure of atmosphere, it is not easy to see how a race even more advanced than ourselves could maintain itself alive under serious lack of an element so vital to existence. Both Wallace, the great biologist, and Arrhenius, the eminent chemist, but biologist, astronomer, and physicist as well, both reject the habitation theory of Mars regarding the so-called canals as quite like the luminous streaks on the Moon, that is, cracks in the volcanic crust caused by internal strains due to the heated interior. Wallace, indeed, argues that the planet is absolutely uninhabitable. The asteroids, or minor planets? We may dismiss them with the simple consideration that their individual masses are so insignificant and their gravity so slight that no atmosphere can possibly surround them. Their temperatures must be exceedingly low, and water, if present at all, can only exist in the form of ice. Jupiter, the giant planet, presents the opposite extreme. His mass is nearly 1,000th part of the Sun's, and is sufficient to retain a very high temperature, probably approximating to the condition we call red hot. This precludes the possibility of life at the outset, although the indications of a very dense atmosphere many thousand miles in depth are unmistakable. Of Saturn, 1/3500th the mass of the Sun. Practically the same may be said. Proctor thought it quite likely that Saturn might be habitable for living creatures of some sort, but he regarded the planet as on many accounts unsuitable as a habitation for beings constituted like ourselves. Mere consideration of surface temperature precludes the possibility of life in the present stage of Saturn's development, but the consensus of opinion is to the effect that life may make its appearance on these great planets at some inconceivably remote epoch in the future, when the surface temperature is sufficiently reduced for life processes to begin. Discoveries of algae flourishing in hot springs approaching 200 degrees Fahrenheit make it possible that these beginnings may take place earlier and at much higher temperatures than have hitherto been thought possible. A century ago, when the ring of Saturn was believed to be a continuous plane, this was a favourite corner of the solar system for speculation as to habitability. But now that we know the true constitution of the rings, no one would for a moment consider any such possibility. Conditions may, however, be quite different with Saturn's huge satellite Titan, the giant moon of the solar system. Its diameter makes it approximately the size of the planet Mars, and although it is much further removed from the Sun, its relative nearness to the highly heated globe of Saturn may provide the equability of temperature which is essential to life processes. Also, the three inner Galilean moons of Jupiter, especially 3, which is about the size of Titan, are excellently placed for life possibilities as far as probable temperature is concerned, but we have of course no basis for surmising what their conditions may be as to air and water, except that their small mass would indicate a probable deficiency of those elements. Uranus and Neptune are planets so remote, and their apparent disks are so small, that very little is known about their physical condition. They are each about 1/3 the diameter of Jupiter, and the spectrum of Uranus shows broad diffused bands, indicating strong absorption by a dense atmosphere very different from that of the Earth. Indications are that Neptune has a similar atmosphere. It is possible that the denser atmospheres of these remote planets may be so conditioned as to selective absorption that the relatively slender supply of solar heat may be conserved, and thus ensure a relatively high surface temperature when the Sun comes into control. If our theories of origin of the planets are to be trusted, we may rather suppose that Uranus and Neptune are still in a highly heated condition, that life has not yet made its appearance on them, but that it will begin its development ages before Saturn and Jupiter have cooled to the requisite temperature. Comets? In his Lettres Cosmologiques, 1765, Lambert considers the question of habitability of the comets, naturally enough in his day, because he thought them solid bodies surrounded by atmosphere and related to the planets. The extremes of temperature at perihelia and aphelia to which the comets are subjected did not bother him particularly. After calculating that the comet of 1680, being 160 times nearer to the Sun than we are ourselves, must have been subjected to a degree of heat 25,600 times as great as we are, Lambert goes on to say, whether this comet was of a more compact substance than our globe, or was protected in some other way, it made its perihelion passage in safety, and we may suppose all its inhabitants also passed safely. No doubt they would have to be of a more vigorous temperament and of a constitution very different from our own. But why should all living beings necessarily be constituted like ourselves? Is it not more infinitely probable that amongst the different globes of the universe a variety of organizations exist, adapted to the wants of the people who inhabit them, and fitting them for the places in which they dwell, and the temperatures to which they will be subjected? Is man the only inhabitant of the earth itself? And if we had never seen an either bird or fish, should we not believe that the air and water were uninhabitable? Are we sure that fire has not its invisible inhabitants, whose bodies made of asbestos, are impenetrable to flame. Let us admit that the nature of the beings who inhabit comets is unknown to us, but let us not deny their existence, and still less the possibility of it.
Little enough is really known about the physical nature of comets even now, but what we do know indicates incessant transformation and instability of conditions that would render life of any type exceedingly difficult of maintenance. A word about Sir William Herschel's theory of the Sun and its habitability. He thought the core of the Sun a dark solid body, quite cold, and surrounded by a double layer, the inner one of which he conceived to act as a sort of fire screen to shield the Sun proper against the intense heat of the outer layer, or photosphere by which we see it. Viewed in this light, the Sun, he says, appears to be nothing else than a very eminent, large and lucid planet, evidently the first, or, in strictness of speaking, the only primary one of our system. It is most probably also inhabited, like the rest of the planets, by beings whose organs are adapted to the peculiar circumstances of that vast globe. But physics and biology were undeveloped sciences in Herschel's days. Herschel knew, however, that the stars are all suns, so that he must have conceived that they are inhabited also, quite independently of the question whether they possess retinues of planets after the manner of our solar system. This again is a question to which the astronomer of the present day can give no certain answer. So immensely distant are even the nearest of these multitudinous bodies that no telescope can ever be built large enough or powerful enough to reveal a dark planet as large as Jupiter, alongside even the nearest fixed star, whatever may be the process of stellar evolution. There doubtless is an era of many hundreds of millions of years in the life of a star when it is passing through a planet-maintaining stage. This would likely depend upon spectral type, or to be indicated by it, and as about half of the stars are of the solar type, it would be a reasonable inference that at least half of the stars may have planets tributary to them. In such a case, the chances must be overwhelmingly in favour of vast numbers of the planets of other stellar systems being favourably circumstanced as to heat and moisture for the maintenance of life at the present time. That is, they are habitable, and if habitable, then thousands of them are no doubt inhabited now. But astronomers know absolutely nothing about this question, nor are they able to conceive at present any way that may lead them to any definite knowledge of it. There is, indeed, one piece of quasi-evidence which might reasonably be interpreted as implying that it is more likely that the stars are not attended by families of planets than that they are. End of chapter 34.